हेलो हेलो हाँ हाँ तो वो लोग रिजेक्ट हो गया तो कोई नहीं मेरे पास भेज दो
So, hello, good
Yes.
evening, good afternoon, everyone. So, we are just assembling here for the second day's talk, and yeah, we are having Professor Ananda Dasgupta with us. We will be continuing with the third lecture of the series, and talks will be continued from yesterday. I have already sent the copies of video recordings to everyone. So you must have got it by now. If you are having any problem, you can write to my Gmail ID, not to any other ID, my name and in the Gmail ID, if you are having any confusion. And now I am leaving the platform to Professor Dasgupta. He will start.
Okay, so I can so I can start now, right?
Yeah, sure.
Okay, thanks. So before I commence, are there any questions from last day? Any very pressing
No.
questions, that is, or just general discussion? If not, let's start with the next topic, which is actually the most important topic for us when we try to use physics, group theory in physics. The topic today is representation theory. Basically, how you use group theory, especially today we are going to talk about finite groups primarily. Uh, how would you use them in various physical applications? And the route to that is representation theory. So let me just start my presentation first. Okay, so the presentation is ready. Let's go to the slides. Okay, so basically, yesterday's talk was primarily about abstract notions of group theory. There, of course, are practical applications, but most of them were stated at least in an abstract manner without reference to any. Although we did refer to specific groups, most of the results that we talked about could be used for any group whatsoever, at least, say, finite groups and so on. Today, what we are going to do is take a look at representations first. And this is where the connection with physics becomes even more apparent. This is the notion of group action. A group G is said to act on a set. I'm calling the set M. If there exists a map from G cross M to M, this is really simply a way of saying, give me a group element, give me an element in the set M, and I will just tell you how the group element acts on the element of the set M. So it maps G comma M, an ordered pair, G from the group, small m from capital M, into a new element of capital M called Gm. Now, before I go on to the formal part of the definition, which is, of course, these two properties, let me remind you that we have already seen such group action. Like we saw what happens when you apply the symmetry group or the elements of the symmetry group of the equilateral triangle on points of the equilateral triangle. There, our set M was basically the set of points in the equilateral triangle, and the group G was, of course, the symmetry group. And we found out what happens to each point or any arbitrary point when you apply each of the elements one after the other. And this map has to have some properties in order for it to qualify as a group action. The first property is that the identity element of the group should do nothing to any point M. So every point in the manifold or set capital M will stay unchanged when you apply E on it. So EM is the same as M, which of course completely squares with our notion of E being doing nothing. And what is important here is this: when you take any two elements G1 and G2 from the group G and you apply this, that is, you do G2 first on M and then you apply G1 on the result has to be the same as G1, G2 acting on M. You should realize that that's exactly the rule that we use to figure out the multiplication table for the group that we talked about, the group of symmetries of the equilateral triangle. All we did was we first applied B, let's say, on a particular point P, and then we applied A, and the result was something, but we knew that it has to be BA acting on P. And whatever that turned out to be, BA has to be equal to that. That's how we built up the multiplication table yesterday. And that was basically based on the fact that you have this basic property in every group action. Now, if this group action is on some concrete mathematical or physical system, this gives us a concrete realization of the group as opposed to an abstract set of objects which obey some multiplication rule. So we have already seen such realizations. After all, once again, let's talk about the symmetries of the equilateral triangle. The 6 operations that we were talking about are concrete realizations of an abstract group. 6 objects, E, A, B, C, D, F. I don't care what they mean. At the abstract level, I don't care what they mean. All I know is that the multiplication table looks like that. That was the abstract version of the group. The concrete realization is, of course, via the fact that A, B, and C are reflections about medial lines, and D and F are rotations. Now, the action that you have is also called a representation of the group. This is just, well, there's a bit of ambiguity in the terminology. Different people use slightly different things, mean slightly different things when they say representation. But let's move on to more concrete things where everybody agrees. So one kind of representation that everybody talks about are so-called linear representations. They're also known as operator representations. For that, of course, what you need is an arena on which the operators can act. So you need a linear vector space to begin with. So you have a V, which is a linear vector space. And of course, yesterday we saw that if you take all the linear operations that you can do on V, they don't form a group, of course, because there are non-invertible linear operations possible. But if you just take all the non-singular linear operators, which means operators which do have inverses, which act on the set V, this set is called the general linear set acting on V. We saw special cases of that, GLNR, GLNC. These were basically sets of non-singular operators acting on R to the N or C to the N. But GLV is in general the set of all non-singular linear operators acting on any vector space V. They form a group. And a linear operator representation of any group capital G is a homomorphism from capital G, the group, to gamma, where gamma is a subset of GLV. So basically you are saying that for every group element small g in capital G, we will have an operator, which is a member of gamma. And this representation has to be such that if G1 maps to LG1 and G2 maps to LG2, then G1, G2 has to map to LG1, G2, of course, but LG1, G2 must be the same as LG1 times LG2. So that is where the homomorphism comes in. Whether you apply the map first on G1, G2, or whether you compose first, form G1, G2 first, then apply L, or apply the map first on G1 and G2 to get LG1 and LG2, and then multiply, you get the same result. So this is the basic demand that you are making, that the map L, which maps from capital G to gamma, where gamma is just some subset of GLV. So all the gammas, all the results of gamma, all the results that you get in gamma, that is L of small g, has to be a non-singular linear operator. And LG1, G2 has to obey this particular property. That's the most important property that we have. So before we go any further, let me just give you a reason why we should be worried about, or we should really think about such representations. Let's think of a very special thing that happens all the time in physics. Suppose we have a set of coordinates which we use to describe a physical entity. Of course, you will have numbers describing the physical entity. How many numbers? That depends on what kind of physical entity you have, right? If it's a scalar, you need only one number. If it's a vector, you will need 3 numbers. If it's a tensor of rank 2, you will need 9 numbers, and so on. When you change your coordinate system, these numbers will change, right? And the beauty of tensors essentially is that each of these numbers will change linearly. There will be a linear map which acts on the current numbers to give you the new set of numbers. So every rotation has a corresponding linear transformation. Now, and this is important, if I do one rotation after another, the resulting thing is, of course, a single rotation. Now, it is true that the numbers which describe a physical entity may very well depend on the coordinate system. So it will depend on whether you rotate your coordinate system or not. But the numbers should not depend on how you got to your final coordinate system. Whether you did it in one step, that is, you did only rotation R2, or whether you did it in 2 steps. Suppose I did R2 first, then I did R1. That's one way of doing it. Another way of doing it is doing R1, R2 in one go. That would be do R2 first, then do R1, right? So the point I'm trying to make is, if I do it in 2 steps, the linear transformation should be a composition of LR2 followed by LR1. So LR1, LR2. When I say followed by, remember the one which is followed, which comes after, is written on the left. So LR1, LR2. That's one way of getting from the original coordinate system to the final one. The other way is simply by applying a single transformation, LR2R1. The thing is, whether I do it in 2 steps or whether I do it in 1 step, I should end up with the same result, which is why LR2R1 should be equal to LR2 times LR1. So this shows why we have this homomorphism demand. Whether I do one group operation after another or I do a single group operation, the final result should really be the same. And in particular, if the map is also 1-to-1, that is 2 different group elements mapped to 2 different operators, then you say that the representation is faithful. But there are plenty of representations which are not faithful. It might very well be that multiple group elements map onto the same final operator. Now, why are linear representations so useful? A, because they happen very often in physics, but more importantly, because once you go to linear representations, you can use the full power of linear algebra to calculate various results. And that is what we are really going to try to do today. And one of the first things we know about linear transformations, I hope everybody here knows this, that you can represent a linear transformation on a vector space by a matrix by choosing an ordered basis. So this is a general statement from linear algebra that any linear operator T on a finite dimensional vector space V can be converted to a matrix, or can be represented by a matrix, to be more precise, by choosing an ordered basis, some set of vectors E1, E2 up to En, and defining the matrix through this. T acts on a vector to give a vector, so T acts on EI, a given basis vector, the ith basis vector, to get a vector. So every vector can of course be expanded in the basis, so I can always write TEI as sum of E1 E2 times something plus E2 times something plus E3 times something, and so on. The coefficients of this expansion are the matrix elements, and the coefficients are labeled MJI. Now I want to know, is there anybody here who does not know why these are called MJI and not MIJ? That this rule for going from the basis, the action of a linear operator on a basis, to the expansion to the matrix has this MJI rule. That is, J and I appear to be reversed in order. Is everybody familiar with that? Okay. That of course means if somebody is not familiar with that, please speak up. But this is elementary linear algebra. I'm pretty sure most of you have seen this before. Okay, for the time being, just let's remember this as a basic rule, that you have to have MJI EJ. And of course, that was for any linear operator. But if you have a linear representation of a group, then every group element corresponds to a linear operator. So for every small g, you have a LG. And if you apply LG on EI, you are going to get its corresponding matrix, which I'm going to call D of G. And the matrix elements are DJIG here, which can directly read off. So the important thing is the rule that LG1 G2 is LG1 times LG2, that translates to DG1 G2 is DG1 times DG2, where this is just plain old matrix multiplication. Remember that although these both look like multiplication, they actually mean different things. Here LG1, LG2 means do LG2 first, apply LG2 first on the vector, and then you apply LG1. So it's successive applications of a linear operator. Here, of course, this is plain matrix multiplication using the row by column rule for matrix multiplication. The important thing is, that is precisely why you have this MJI rule here. That ensures that when LG1, LG2 turns out to be LG1, G2, then DG1, G2 also turns out to be DG1 times DG2. So now let us just see this in action in a particular example so that we can sort of be sure of what all this means. So we are going to fall back on our old friend, the group S3, or the set of symmetry operations acting on a triangle. And where the vector space V, it has been hidden behind this icon here. V is R2, the plane. So of course, on the vector space V, you can put down basis vectors E1 and E2. And what we will do is we will apply each of the linear operations LE, LA, LB, and so on in succession on these basis vectors, find out what happens to the basis vectors, and from that construct the matrix. So how does this work? Well, LE, for example, if you do, LE is the linear operator corresponding to doing nothing, which of course does nothing. E1 stays E1, E2 stays E2, right? LE1 is E1, LE2 is E2. And the matrix that you can write down here is rather trivial, but you can formally write down the matrix using our rule by saying result LE1 E1 is 1 times E1 plus 0 times E2. The 1 and the 0 forms the first column. Remember, it's a column, not the row. First column of the matrix DE. So 1, 0 goes down the column. Here you have 0 times E1 plus 1 times E2. So 0, 1 is the second column. So what you get is this. Of course, no surprises there. That's our familiar identity matrix. Now, because this particular matrix is symmetric, you didn't really see whether using the row as opposed to the column really made a difference. Right? Remember 1 and 0 here, 1 into E1 plus 0 into E2 were actually used to write down the column and not the row. But that didn't make a difference ultimately because this matrix is symmetric. So as long as the matrix is symmetric, it will not make a difference whether you write it this way or that. But since all matrices are not symmetric, the rule is important. So let's look at the next operator. This is which is the operator corresponding to A. So A is reflection in this line. So what does LA do to E1 and E2? Well, if you reflect in this line, which is of course the same as this line, LA E2 is the same as E2. LA E1 on the other hand has changed sign. So it has become minus E1. So once again, writing down the matrix here is straightforward. It's going to be minus 1 times 0 for the first column and 0, 1 for the second column. Again, this is symmetric, so frankly, you didn't see the difference. But still, this is the matrix that you have for D of A. This one is slightly non-trivial. You are reflecting along this line. That's your B. This is this dashed line here. Dashed red line is the line of reflection. So E1 reflects in that becomes LB E1 is the matrix. We are trying to find out the effect of B or the operator corresponding to B. So LB E1 is here, and E2 on reflection on this dashed line goes here. So that's LB E2. It takes a bit of simple trigonometry to figure out that these are half and √3/2 factors respectively. So I would urge you all to check that I'm doing this right, but this is pretty straightforward. So these are the combinations. So what you get is half root 3 by 2 this half and this root 3 by 2 for the first column, root 3 by 2 minus half for the second column. So written down dB. TC done very similarly. I'm not going to go into repeating this every time because you should be able to figure it out yourself. Let me just point out that if you rotate through 120 degrees, that's LD. So E1 goes here to LD1 and E2 goes to LDE2. Now you get this as the resulting vectors. So minus half root 3 by 2 form the first column and minus root 3 by 2 minus half forms the second column. The reason why I'm specifying or especially talking about LD is as you can notice, DD is not symmetric. It's actually, it has a change of sign between these two elements, which is why you have to be careful here. You have to go down the column. So minus half root 3 by 2 is the first column, minus root 3 by 2 minus half is the second column. That rule has to be taken seriously for this.
Excuse me, sir.
Yeah, go ahead.
So actually, if the things are cyclic, then how does it matter that we are specific about rho and coulomb?
What are cyclic? Things are not really cyclic.
We have total symmetry and non-symmetric also, and things are cyclic. Means we can start from any
No, what are
point.
cyclic? What are cyclic? No, the point is the
the whole-
matrices of DT is a particular matrix which stands for the represent. Look, if you interchange the rows and columns of a matrix and the matrix changes, then you end up with a different matrix. As simple as that. I'm not sure whether I understand what you are calling cyclic here. Of
Okay,
course,
sir,
if you were to, okay, maybe I think I've got you, because the next one, look at DF. DF essentially is the other one.
Yes, sir.
But you have to be careful. You cannot really confuse D with F. They're two different things, right?
Okay, sir.
If you had
Thank
mixed
you.
up the rows and columns, you would have ended up with DF instead of DD. That's all.
Okay, sir. Okay, sir. Thank you.
Okay, that's it. Nothing else. And then
Yes,
then the problem will be the group multiplication rule would not work for these matrices. Say we had BA equals F. If you had taken for these matrices, if you take DB and DA and multiply them together, you will get DF. If you had got not you obeyed the row column rule properly, you would have ended up with a different matrix. In fact, you would have ended up with DD in that case. That of course would have been wrong, right? It wouldn't have reflected the multiplication rule, which is what you want to do. So, okay, before I go further, are there any other questions? So we have basically said that for every group element, there will be a linear operator, and these linear operators will have to respect the group multiplication rule. That's why you demand that this is a homomorphism. LG1, G2 has to be LG1, LG2. And given a linear representation, you can also go over to a matrix representation just by choosing a basis. Okay. So in physics and chemistry, very often we deal with matrix representation so much that we often forget that the matrices are really representatives of some linear transformation behind the scene. Okay. But of course, there's one very important thing about the matrix representation. The same linear transformation will look very different or will produce a very different matrix if I were to use a different basis, right? A choice of basis is implied in this definition. You're using a particular basis, right? To change your basis, you're going to get a different matrix. And that is what we are going to look at next. This is our topic called equivalent representations, or more precisely, equivalent matrix representations. Well, the point is, there are infinitely many possible choices for an ordered basis on V, right? You didn't have to use E1, E2. You could have used any two vectors which are not collinear in the last example, and you would still have had a basis for R2. In any vector space V, you have infinitely many choices for the basis that you can use. In particular, if S is a non-singular matrix and you apply Sji, Ej on all the basis vectors, so basically E prime 1 is S11 E1 plus S21 E2 plus S31 E3 up to Sn1 En, and do that for every one of i's values from 1 to 3 up to n. get n new vectors. And if S is a non-singular matrix, it's very easy to check that then E prime I will also be linearly independent, n in number, so they will also give you a basis. So this is basically how you change from one basis to another. Now, if you change the basis, of course the matrix will change. So because now your LG will have to act not on the E1, E2, E3, but on E1 prime, E2 prime, E3 prime. So let's apply LG on EI prime. What will happen is, since EI prime is this, SGI, EJ, and SGIs are just numbers, EJs, remember, are the vectors. So the LG will simply ignore the SGIs, the linear operators, so they will just jump across the numbers and go and hit the vectors. So LJ, EG. Now LG, EJ, we already know what they are. They give you the original matrix elements that we had talked about a while ago. So LG, EJ can be expanded in terms of the old basis vectors, E1, E2, E3, En, using the rule that we just wrote down, DKJG, EK. Remember, it's DKJG. That's the order. Once again, this is just a column as opposed to row rule. Okay. Now, this gives us an expansion of the result of LG acting on EI prime, the new basis vectors, but an expansion in terms of the old basis vectors. That will not do. I want, since I'm going to change my basis, I want to expand LG EI prime in terms of the old, not in terms of old basis vectors, but in terms of new basis vectors. But that's easy. All you need to do is look at the fact that EK, this SGI and DKJG are just numbers, so you can just move them out. Remember, they are just numbers. SGI is number, DKJG is also a number. One number for every group element, but still a number, all the same. So you can just move it out of the sum here and do a sum over J and K, but replace EK by this sum, which is just the inverse of going, you went from EJ to EI prime using S, you go back from EJ to EI prime, you go back from EJ to EI prime using the inverse. So that's all there is to it. And then when you combine them all together, this is what you get. LG EI prime is simply going to be S inverse MK times DKJG SJI summed over JK equal to 1 to N. And finally, the results multiplied by EM prime summed over all M1s. Okay. Now, you must have realized that I've changed the order in between. I've moved the DKJG before the SJI, and I've also moved the S inverse MK in the front here, to the front here. But that's easy to understand, right? All we are doing here is noticing that we are putting the column index of the matrix in front here and the row index, you're matching them, which is exactly how you do matrix multiplication. So this thing in the bracket here ultimately is the mith element of what? Mith element of the product matrix S inverse DGS. So that is our final result, that when you apply LG on EI prime, you can expand the result in terms of the new basis vectors, of course, and that will give you the new matrix in this new basis. But the new matrix in this new basis is simply equivalent to the matrix in the old basis. It's a similar transformation that we have done, S inverse DGS. Okay, so the matrix representation in the new basis simply becomes D prime G is S inverse DGS. Now this is a similar transformation, but it's something slightly more than just an ordinary similarity transformation. In a similarity transformation that you do in the theory of matrices, you take a matrix, you take another non-singular one, S, and you do S inverse AS. Here, you don't have one matrix. Remember, DG is one matrix for every group element. So you have as many matrices here as group elements. And you're applying the same similarity transformation on all of them. And that gives rise to a bunch of new matrices, which are going to be representations for the same group, but with a changed basis. Now, when I claim that this is going to be a matrix representation, I should really check whether d prime g1, d prime g2 does give me d prime g1, g2. Does it? The answer is straightforward. You can just check. What is d prime g1, g2? By our rule right now is simply S inverse dg1, g2, S. But D, remember, is a representation. So dg1, g2 has to be dg1 times dg2, this product. And now, well, the rest is straightforward for everybody who has done any linear algebra. You would know that the immediate thing that you would do here is put a S and a S inverse in between the dg1 and dg2. And if you do that and use the fact that matrix multiplication is associative, you can multiply these three together and these three together, and you end up with d prime g1, d prime g2. So the new matrix representation is really a honest to goodness, genuine matrix representation. If you take the matrix corresponding to g1, multiplied by the matrix corresponding to g2, you do get the matrix corresponding to g1, g2. But you should realize one thing: the equivalent representations that we have found have no new information. They have exactly the same information as the original representation. All that you have done is change your basis, and the basis is an artificial imposition on the vector space, right? The vector space doesn't come with a basis marked on it. It's just a bunch of vectors which you can add or multiply with. The basis is something you introduce in order to be able to then deal with simple numbers rather than abstract vectors. So once we have done this, we should realize that this change of representation is a perfectly genuine or valid thing to do, but it does not really change the physics or the mathematics behind the subject at all. So two equivalent representations have the same information, and we will later essentially treat them as the same. And this is exactly what we mean by equivalent representations. Representations, two matrix representations which can be obtained from the same linear representation, that is operator representation, just by applying or just by changing a basis, or at the matrix level just by applying the same similarity transformation, S inverse dgs, to every one of the dgs. Okay, this is a nice time to... yeah, go ahead.
Yes, sir. So here d prime is acting on the vector represented in the primed basis, right?
Well, d prime is actually, first of all, the matrices don't really act on the abstract vectors. What you can, of course, do is use the basis to change the vectors into column vectors. Okay?
Yes, so if I represent the my vector in my primed basis,
then you get a different column vector, right?
Yes, and then the appropriate representation of the operator would be the primed matrix.
Yeah.
In that case, shouldn't the expression be SD S inverse?
No, that's because E prime is SE. Just that's again, okay, I will let you to worry about this. This is basically because usually when you say change of basis, you often talk about how the components change. Okay. That depends on what you are using as your change of basis matrix. Here the change of basis matrix I have used is literally a change of basis matrix. The new basis vectors are expressed in terms of S times the old basis vectors. Okay. This is the rule that we have used. You would realize, okay, just think about it a bit. You would realize that if this is your change of basis, then because the vector stays the same, the components will change according to inverse of this. So that rule that you were saying, SD S inverse, would have been because then this would have been the S inverse. That's all. I do get your point. But that depends on which one you're calling S.
I got what you're saying.
Okay. Yeah. But that's a good catch. If you had used the matrix which changes coefficients, then this would have read SD S inverse. Anyway, the whole point is there is a non-singular matrix S somewhere. Of course, if S is non-singular, so is S inverse. You could just use them interchangeably as well. But anyway, as long as you're saying it's a change of basis, this is the way it has to change. If you're saying it's a change of coefficients, then it will be SDS inverse. I hope everybody else is clear about this discussion. And it didn't confuse anybody. But you have to be careful about what is this S doing. It's changing the old basis vectors into the new basis vectors. That's all that's important here. Okay. Now let us give some examples of representations. In fact, I've already given you one example of both linear representation and matrix representation. That's the two-dimensional representation or the 2x2 matrix representation that we just constructed. But let's talk about one-dimensional representations in general. One-dimensional representations means the vector space is one-dimensional, which means all vectors are basically multiples of a given vector, which of course means that the only thing you can do linearly on such a space is multiply by a number. Or the matrix representations are all 1x1 matrices, which are just, well, a mathematician might make a distinction between a 1x1 matrix and a number, but we usually don't. Even mathematicians don't, come to think about it. So basically, these are representations of group elements by just numbers. Now, every group has at least one 1D representation, and everybody knows that representation. That representation is called the identity, also known as the trivial representation. Not to be confused with the identity element of a group. This is the identity representation, which simply says replace every group element or associate every group element with a single number, the number 1. So that's it. Notice that this is a perfectly valid representation because if you do dg1, g2, that dg1, d2 is of course 1, but that has to be equal to dg1 times dg2, but 1 times 1 is 1. So it's as simple as that. Although this is a very simple thing and trivial thing mathematically, it's very important for physics. Can anybody tell me what this representation is in the language of physics? Say, for the rotation group, let's say.
It's a symmetry of some sort.
What? No, it's a look, we are talking of a object which you can describe by one number because it's a one-dimensional vector space. And what happens to that object when you rotate your coordinate system? dg acts on it. dg is 1. So what happens to that?
It doesn't change.
Doesn't change. So what is this kind of object called?
It's a constant under the symmetry. It's invariant.
Okay, that's true. But we all have a name for this kind of object, right? They're called scalars.
But invariant.
Invariant, yes, but specifically if you think of rotation group, these invariants are called scalars, right?
Yes.
All the scalars that we have learned about, they are basically just these quantities, things which change according to the identity or the trivial representation of the rotation group. By the way, even for other groups, very often this is called the scalar representation. Simply because, at least physicists often call this a scalar representation. Simply because that's what scalars do, they don't change. Now, the important point is there are many important physical quantities which are really scalars. And by the way, before I go any further, let me ask you one question. This is for everybody in the audience. Can you think of any one component object which is not a scalar? An object which is described by a single number which is not a scalar. Okay, think about it.
Sir, 2i.
2?
2i cap. Can that be treated as vector?
Well, 2i cap is of course a vector, but the x component of vector is a single number, but it's not a scalar. Why not? Because if you transform, if you rotate your coordinate system, suppose you know a vector has an x component of 2, but you don't know anything about its y component. Can you find out its x component in a rotated coordinate system? I know the x component of a vector is 2, but I have no knowledge about its y component. Can I find out its even its x component? The one component I knew in a new coordinate system?
No, sir.
You can't, right? That is why x cannot really doesn't come alone. You always have to talk about x and y. In fact, that's why in 3 dimensions, it's actually 3 dimensions. You have to talk about x, y, z together. And that is precisely the reason why once Lorentz transformations came in and we talked about the rule for going from one inertial observer to another, involving those Lorentz transformation laws which Einstein gave us. We had to say that space-time is four-dimensional, not because there were four numbers involved, but simply because it was impossible to find out t prime, for example, without knowing x, y, z, and t. In the classical world, before Einstein, if you knew t, you would know t prime. T and t prime were the same, right? You did not need to know x, y, z for that. But Einstein gave us a transformation which said to find out x prime, y prime, z prime, t prime, each one of them, you need to know x, y, z, and t. Which is why you have a four-dimensional object, not a 3+1 situation. Of course, it's still 3 and 1 very different, but that's a different issue altogether. We just think about what I was asking is, can you think of a single component which completely describes a physical system, a single number, a physical system which can be described, or physical object which can be described by just one number, which is not a scalar? Can you think of such a thing? Think about it. We'll come back to that in the end of the lecture. But let's talk about other 1D representations possible. Now, if you have a matrix representation, in some, okay, the size of the matrix, of course, will depend on the dimensionality of your space. So if you are in an n-dimensional vector space, you'll get an n by n matrix. But every matrix representation will give rise to a 1D representation automatically, just by doing this. Take your DG matrix, DG, which is a matrix, n by n matrix, find its determinant. And that will give you a one-dimensional representation. Well, that will definitely give a number corresponding to every G. But why is this a representation? Simply because of the basic property that if you multiply, say, what is D1 of G1, G2? D1 of G1, G2 is determinant of D of G1, G2. And what is D of G1, G2? DG1 times DG2. And you all know that when you multiply matrices, the determinants multiply. So D1, G1 times D1, G2 is what you will get. So if you have any matrix representation, any matrix representation whatsoever of a group, and took the determinant of every one of those matrices, you will end up with a 1D representation for that group. If we can just go back a bit and look at our example matrices. So E had this 2 by 2 matrix, right? The determinant was 1. A, what is the determinant of this? -1. B, -1 again. C, -1 again. D, just carefully calculate, you will get +1. Should not come as a surprise. This is a reflection, this is a rotation, and rotation should have determinant of +1. Then comes F, again determinant +1. So the 1D representation corresponding to this rule that we just spoke about for this particular group happens to be assign all the rotations +1, which includes, of course, 0 rotation, which is the identity. Assign all of them +1, assign -1 to all the reflections. You have got a 1D representation, which is different, by the way, from the trivial representation. This group also has a trivial representation. Just say every one of the group elements correspond to the number 1. You've got the trivial representation. But this one is different. So I've got 2 1D representations already for this group S3. Okay, let's go back now, or go forward rather. And now let's talk about another kind of representation which is also very, very important in physics. It's called function space representation. For that, you have to understand what a function space is. I'm pretty sure most of you already know this, but let's just say that you have a vector space V and curly F, this symbol that I have here, is a linear space of functions on it. Now, what does this mean? Well, a function on V here just implies it's a map from V to R or C, depending on your situation. Usually it will be either R or C. So to be specific, let's just say R for the time being. So a function is a map which maps a vector into a real number. What is this linear space of functions? This is not, by the way, this is not space of linear functions. The order matters. When I say linear space of functions, I mean these functions which apply on a vector space to give you numbers. Can you make a vector space out of those functions? Point is, can you add the functions together? Can you multiply them by numbers? The answer is, of course you can. You can just define f1 plus f2 simply by saying f1 plus f2 does to v what f1 does to v plus what f2 does to v. So f1 plus f2 acting on v is f1v plus f2v. And what is a times f1, where a is a number? You just say it's a function whose action on v is a times f1v. So that's how you define the linear space of functions on it. Okay. And the important thing is, every time you have a linear operator t on v, this induces a non-singular linear operator ot on, okay, curly v. Oh, sorry, this is a mistake. This should be curly f. So the point is, you have a t which acts on vectors to give you vectors.
Is
Oh,
the screen sharing stopped, or I am not able to see the screen?
Yeah,
No,
Professor
sir.
Dasgupta. Professor Dasgupta, your screen is not on.
Has it not been on for a long time?
No,
It was
only for
just
2-3
now.
minutes.
Yeah, I think my presentation stopped somehow. Okay, let's go back. Yeah, this,
Hello. Oh. $404D না সে থাকুক আমি তো এক লগেই পাঠাইছি পুরা তো তোমার ইয়ের ভিতরে আছে কি তা কয় মানে না আমার সব এক লগে হ্যাঁ সব আছে এখানে দাঁড়াও দেখি দাঁড়াও ইউডিসি মার্কার 404D প্রথম ফাইলই 404D তোমারে যেটা পাঠাইছি আমি জিপ ফাইল খুলো এটা প্রথম ফাইলটা 405D 404 না ওকে 404 আমি দেখি দাঁড়াও 404
okay, I'm back. I hope everybody can see my presentation. Okay, see the fact that I'm presenting.
405 থেকে 404 আমার চোখে পড়েন না দেখি
So is my presentation visible now?
Yes, sir.
Yes.
Okay. So where was I? I think
It's not
Okay,
properly,
anyway,
make it a full screen.
yeah, I will make it full screen. I'm just asking whether you can see it.
Yeah, it is visible, but
Okay, fine. So let's start again. The basic idea is that you have this linear space of functions whose elements are functions f from v to some real numbers. And the important basic theory, again, nothing to do with group representations, but this is basic linear algebra, that if you have a non-singular linear operator t on v, this will induce a non-singular linear operator ot on curly f. This is a typo, this should be curly f. That is, ot will act on a function to give a new function. Otf, the new function, is defined to be, of course, what is a function? A function is something which associates a vector with a number. So what is this OTF? I have to tell you what it does to V, a vector. And the rule is, it's F acting on T inverse V. So this is important. It's not F acting on TV, as you might think. But you apply the inverse transformation on the vector argument that you get supplying, and then apply function on that. That's how you get the value for the new function OTF. Now, why is this T inverse? There are two reasons. One of them is physical. Let me give you the physical argument first. Suppose I have I have some body on which there's a temperature distribution, and we are talking about the function that I'm talking about assigns to every point a temperature. Now, let's say I apply a transformation on this body. Let's say I rotate it. And now I want, again, to apply, to get the temperature distribution. If I've rotated the body, will I have the same temperature distribution as before? Temperature is a scalar. fine. It doesn't change when you rotate your coordinate system. But if I rotate the body which has some temperature distribution, will the new temperature distribution be exactly the same as before? Yes or no?
It depends. Sir.
No, sir.
In general, no. Of course, if the temperature distribution had been isotropic, same in all directions, then rotating it would not make any difference. But if the temperature distribution is not isotropic, and suppose it had a peak somewhere, when you rotate, the peak moves somewhere else, right? So the new function which describes temperature after the rotation, what will it be? After all, the points are the same, they have just turned around. So you want to find the value of the new temperature at a point. You should really find out where this point was before I rotated and what was the value of the temperature there before. So F, think of F as the old temperature distribution and OTF as the new temperature distribution. To find the new temperature distribution at the point V, all you have to do is find where this point V was before I rotated, that is T inverse V. That was where the point V came from after I did T. And what was the temperature there? So this is how any function on a manifold or on a set transforms when you transform points on the set itself. For those of you who are doing high energy physics, for example, you will see this is how a scalar field transforms. Despite the fact that a scalar field does not change, it's an invariant, the scalar doesn't change. But a scalar field actually transforms simply because the points are changing around when you do a transformation. And the value of the scalar field at the new point is actually the same as the old value of the scalar field at the old point. And that's why old function acting on the old point T inverse. That's one way of seeing it. The other way is simply to ensure that this is what will give you a representation. In other words, yeah, any questions? So now, why are we interested in this? Simply because we have a linear operator or a representation by linear operators acting on the vector space. So LG acts on your vector space. So what we can do is, given such a linear representation on the vector space, I can use it to calculate a representation or determine a representation acting on the function space. So RGF, so you have an original function f, RG acts on f to produce a new function RGF, whose value at v is simply f at LG inverse v. So the point is, this is what you can do for every g, and you get up with new operators on a new space. The space, of course, is curly f, and on this space you get a new bunch of operators which will work. So just to illustrate that, let me give you one example again. Okay, here what we have done is I'm going to skip this simply because I've already told you what this is. This is what ensures that RG1, G2 is RG1, RG2. I think you should take this as the homework. I'm actually going too slow again, so let me speed up a bit. The proof is sort of straightforward, but take some thought. So try to see why this will work, but let's just give an example of this in action. And for this, we will again fall back on our old friend, the group S3, or symmetries of the equilateral triangle. And the vector space we will talk about is R2, vectors of the kind xe1 plus ye2. And instead of talking of all the functions on R2, let's talk of a specific subset, just homogeneous real valued quadratic functions. That is, functions of the kind ax square plus by square plus cxy. Okay. Now, do they form a vector space? Functions of the kind ax square plus by square plus cxy. Of course, to check that, what you need to do is figure out if you add two such functions, do you get such a function? Of course you do. Right? And if you multiply such a function by a number, do you get such a function? Again, you do. And what possible basis functions can you choose here? Can anybody give me the answer to that? Firstly, what is the dimensionality of this vector space? Of functions, not the original vector space. Or take all functions of the form ax square plus by square plus cxy. What is the dimensionality and what possible basis function vectors can you choose?
It's planar, sir.
What? Could you just say that? Plane. You mean two-dimensional?
Yes.
No, because you can easily see that how many independent functions can you have, by the way?
3. Actually 3.
It's 3, right? It's a three-dimensional situation. You can easily see from the fact that I'm saying ax square, where a is some arbitrary number, plus by square, plus cxy, right? So a, b, and c, 3 numbers possible. You can choose as 3 coefficients. And an obvious choice of basis is right there, x square, y square, xy. These are your basis functions. Any function which is homogeneous quadratic will be a linear combination of them, right? Is that okay? So this is a three-dimensional vector space. And so these are the 3 functions. Functions which map xy to x square, xy to y square, xy to xy, x comma y to xy. These are the 3 functions which form a basis of our space. Okay. This is one basis. There could be other bases as well, but right now let's focus on this basis. And let's ask ourselves that if we are given a vector v, then how do we use this? How do we use the linear representation that we already have on two-dimensional vectors to form a representation on the space of functions? Before I go any further, let me also tell you why this is so very important. Functions on spaces are very, very important for physics. And say the wave function, for example, would be a function on x, y, z, right? On a three-dimensional space. And if you have symmetry operations which you do on the 3D space, the wave functions will change. And that will give us a representation involving wave functions. And much of the application of group theory to quantum mechanics essentially involves understanding this function space representation properly. That's just one example. There are many other possible examples, but I'm pretty sure that you will all agree that quantum mechanics is important enough so that if there had been no other applications, even that one would have been important enough to learn about. So let's see in this particular example what happens. To find out the RE, find out the function space representation of the element E, group element E, what we first need to do is apply LE inverse on V, and then find out what happens to F1, F2, F3 under that, and then we can use that to write down our 3x3 matrix. LE inverse, of course, is LE's inverse. That's easy to check. That's LE. No problem. And after all, LE is identity, so it doesn't matter whether you invert it or not. So for under LE, XY stays XY, right? So first, important, remember F1, F2, F3 acts on the coefficients XY. So here the coefficients stay the same. So F1 of course stays the same, so does F2, so does F3. So no surprises really about this. The matrix representation for E in this is just the identity matrix, 3x3 identity matrix. Now let's check what happens to what happens for A. A, remember, is reflection along the vertical line, vertical median of the triangle, which is along the y-axis. So under A, again, it's not A really, it's A inverse that you have to look at. But the important thing is LA inverse is L of A inverse, and A inverse is the same as A. Every reflection is self-inverse. If you reflect twice, you get back to where you were. So LA of V. And under LA, what happens is the X component changes sign, the Y component stays the same, right? E1 becomes minus E1, E2 stays E2. So LA acting on V is minus X E1 plus Y E2. So what happens to F1, F2, F3? Can anybody tell me that? XY becomes minus X comma Y. What happens to F1? What happens to F2? What happens to F3?
Only F3 will be minus F3.
F1
F1 and F2 will stay the same, and F3 will become minus F3. Yeah. F1 will stay the same because, of course, minus X whole square is the same as X square. F2 stays the same because Y square is, of course, Y square. F3 changes sign. So matrix representation here is not the identity matrix, is this with a minus 1 here. Okay. What about B? B is slightly non-trivial, But for B, you have to first work out LB inverse V, which is the same as LBV, because B inverse is the same as B. And LBV, well, V is XE1 plus YE2. We know already what LB does to E1 and E2. We are just using that. So in case anybody has taken notes, you can just go back and look at the expression that I derived. But you can work it out again if you want to. LB acting on E1 is E1 plus root 3 E2 by 2. LB acting on E2 is this. Just plug it in. That says that X and Y actually changes when you do this. X has become X plus root 3 by 2, X plus root 3 Y by 2. That's a coefficient of E1 now. There's a new X and there's a new Y. So now you have a non-trivial change. F1, F2, F3 changes non-trivial. Well, how does F1 change? F1 is square of this after the transformation. So that's X squared by 4, F1 by 4, 3 F2 by 4, plus 2 root 3 by 4 F3. So if you just work out the algebra, this is straightforward. Just square this, multiply these to each other, and you realize that these are the new functions that you get. F1, F2, F3 becomes these new combinations. So new matrix that you have for B, there's a different representation, of course. Same group, same set of operations, same multiplication table, but entirely different representation. This is 3 by 3 representation where DA, DE, DA, DB are given by these. I'm not going to go through all the calculations simply because there's nothing much to learn about from here. It's just algebra. And moreover, it's really no point me telling you what algebraic steps to carry out. It's better that you do it yourself. Okay. But ultimately, you end up with 6 3 by 3 matrices. So this is another representation, a 3-dimensional representation of the same group, which we obtained by using function space representation technique. Can anybody tell me how I could possibly, say, get a, let's say, if I started with homogeneous cubics, x cube, y cube, and so on, what dimensionality would I end up with?
Eight.
Well, how many independent qubits do you have? Remember, it's in 2 dimension. R2 is there's still R2. So x cube and y cube. What else do you have?
X
What other
square
cube?
y.
X square y and
XY square.
xy square. That's it. So 4. So we get 4 by 4 matrices. Okay, another representation by 6 4 by 4 matrices. And the important thing is, you should be able to check this out. If you multiplied DADB, you would get the same as DAB, whatever DAB is. Okay? And if you multiply DBDA, you will get whatever DBA is. That rule is going to be valid. That's how these representations are constructed. So now we are going to talk about one representation which is going to play a very, very important role in all of this. This is called the regular representation. Now, the regular representation is very important because of 2 things. First of all, this is a representation which every group carries on its own back. So you don't have to fall back on any other vector space somewhere else to get this representation, number 1. Number 2, as you will soon see, irreducible representations are actually the building blocks of all representations. You can build all representations together using irreps or irreducible representations. We are going to explain what that is. So, a regular representation is something which gives you every irrep that a group can possibly have. So what exactly is a regular representation? As I said already, every representation is on, or every linear representation, the kind we are talking about, is on some vector space, right? And right now I said, here you don't need any other vector space, you can just use the group itself. How is that possible? The answer is, you can make the group into a vector space. How do you do that? Well, okay, let me ask you a question first. Can you add apples to oranges? Yes? No?
No, sir.
No.
Okay. Suppose I had 3 apples and 2 oranges. That will be 3 apple plus 2 orange, right? And I gave you 4 apples and 1 orange. What will you get? Can you add these? Can you add 3 apples and 2 oranges to 4 apples and 1 orange?
No.
No.
Can't you? You will get 7 apples and 3 oranges, right?
Apples to apples and oranges to oranges.
Yeah, why not? So what is addition? Addition is just a rule which assigns, which takes two inputs, gives an output, has some basic properties. Okay. So the whole point, the reason why I'm saying this is, an abstract group has elements on which a product is defined, right? There is no other operation defined on them. So for example, if you look at our 6 operations, identity and 3 rotations and 3 reflections, would it make sense to say add A to B? That is, add a reflection along one plane to a reflection along another plane. Would it make sense to say that? Or add a rotation to a reflection? Or multiply a rotation by 1.27? Actually, it might seem like it doesn't make much sense. But frankly, as an abstract operation, there's nothing wrong with that. You could just say that, okay, let's take these 6 elements E, A, B, C, D, F and form all possible linear combinations. I don't care what it means. I just say that this is an element of my new vector space, which is called the group algebra, AG. Why algebra? An algebra, as I said yesterday also, an algebra essentially is a vector space on which you have a multiplication rule. Here the group already had a multiplication rule. I make it a vector space simply by defining an arbitrary element of AG to be linear combinations of the group elements. That's it. So, if in case it's a bit confusing, let me just take a look at this possible. Let's say I take this one, C1E plus C2A. Oh, I missed out C, I guess. C4, C. This C is not to be confused with the coefficient here. C5D plus C6F. Let's call this V1. And let's say V2 is essentially the same thing with D1 replacing C1, D2 replacing C2, and so on. Can I define an addition of these 2 things? How would I define V1 plus V2?
I mean, C1 plus D1E plus C2 plus D2A.
Yeah, right.
But sir, what is the field in the background? If you define a vector space, it might be over some field,
Yeah,
right?
so of course. So here the field could be any field whatsoever, but because we are talking of physics application, we would usually stick to either real numbers or complex numbers.
Okay.
Doesn't really matter right now. Any one of them will do for us.
Okay.
Any field will do, but right now we are. And what about alpha times V1? That's just alpha C1 E plus alpha C2 A. Now I will leave you the task of figuring out that this really genuinely defines a vector space, that is, obeys all the basic defining properties of a vector space. And this is an honest to goodness vector space. No problem with this at all. And can anybody tell me what is the dimensionality of this space? This one?
It will be equal to the number of elements in the group.
Number of elements in the group. Right. So for a finite group, it will be a finite dimensional vector space, whose dimensionality will be simply the number of elements of the group. Okay. So for a 6-dimensional group, the one we have here is going to be a 6-dimensional vector space. So going back. So the point is, there is a 6-dimensional vector space in our case, and what are the basis elements? Once again, you can choose arbitrary basis elements. Infinitely many choices are possible, but the obvious choice here is just use the group elements, bus, right? So that's a natural choice for this particular group algebra. So this is what the regular representation gives us. Or this is what gives us a regular representation, to be more precise. So what we have done is we have converted the group into an algebra just by, usually we convert vector spaces into algebra by defining how to multiply group vectors. Here what we have done is we have converted a group into an algebra by going the other way around. You already had a multiplication, you have defined how to add them together. So you use this to define a representation. Okay. So what do we need to do? We need to define a linear operator. Okay, this is L reg, so that's the regular representation. That's why the reg is here. What does it do to every group element here? So to the group G, it's a map from the group G to a subset of AG, of gamma, subset of automorphisms on AG. Maps which map AG or this vector space AG into itself. So for a given group element, you should get an operator. For every group element, you should be able to talk about an operator which acts on AG. Or, as you all know, I'm sure, if you want to specify a linear operator acting on a vector space, all you have to do is tell me what the linear operator does on the basis vectors, which is something we have already used before. So what are the basis vectors we are using? We should be able to say what LG, just forget about the reg for the timing, I'm only talking about the regular representation. So all L's will be L reg. So LG will act on a V. The rule is it will act on V by this, V times G inverse. It will multiply by G inverse on the right. That's the rule. Just check whether this works. Okay, why is this a rule? Let me just explain this to you. So let's say LRG, right now we said this is our operator corresponding to G. Acting on a vector V, it will give me V G inverse. So what I really want is to figure out what LRG1, LRG2 is. I want to check whether this is LRG1, G2. That's the defining property, remember, for a homomorphism. So what is LRG1, LRG2? This is really, you do LRG1 after you apply LRG1, after you apply LRG2 on V, right? So what is LRG2 on V? By our rule, okay, LRG1 is still outside, waiting for its turn to act. But what is this LRG2 on V? That's V G2 inverse. Okay. Then what will LRG1 do to that? This is the argument, right? So we'll take VG2 inverse and multiply that from the right by G1 inverse. That's the way it works. But now by the magic that you all know, this is inverse, G2 inverse, G1 inverse is actually G1, G2's inverse. So this is going to be and since this works for all V, you end up with LG1, LG2 equals LG1, G2. At least. So the regular representation which supplies operator for every group element and whose the job of that operator is to multiply the vector V, which is just some combination of the group elements, by G inverse on the right. This actually gives you a representation. Just to sort of make this a bit more obvious, let me just show what would have happened if we had instead defined L prime G acting on V to be, say, V times G. Let's say we had defined this. Then L prime G1, L prime G2, V would simply be L prime G1, That will wait its turn until L prime G2 gets to act on V. So that's VG2. And then L prime G1 will act on VG2, so we'll produce VG2 G1. But that will be L G2 G1 on V. So we will, or L prime rather, the new map that we are talking about. So this map, which maps G to L prime G, which is an operator which does this, would not obey the homomorphism rule. It will give you L prime G1, L prime G2 is L prime G2 G1, which is different from L prime G1 G2. Got it? So the G inverse that we put in here in the definition, that's actually critical. That allows this to be a homomorphism, otherwise this would not have been a homomorphism.
So,
Yeah.
sorry to interrupt, but
Go
that's
ahead.
only critical because we're right multiplying, right? Why like
No,
wouldn't-
even if you left multiplied, okay. That may look like the case. Let's see. First of all, this is the definition, so you should not argue with it. But still, let's try something else. L tilde G acting on V is, let's say, GV. This would work. That's what you're saying, right?
Yes, sir.
Yeah, this would work. You're right. So if you're left multiplying, you could define it like this. That would give you a different representation. Well, actually, it will not give you a different representation. It will give you a representation which is equivalent to this one. So I'm going to ask you to ponder about that. That if I change my rule from this, that G maps to LG, where LG acts on V by this rule, and G maps to L tilde G, where L tilde G acts on V by this rule, they will both work as representations, but they will not give you two different representations in the sense that it will turn out that L tilde G and LG are similar to each other or are equivalent to each other.
There'll
So
be
you don't really
conjugates,
count
sir.
Hmm?
There'll be conjugates under G inverse, right?
So you figure out how to get the transformation, how to change the basis so that one actually ends up looking like the other. Okay, that's something you can do. You can actually change the basis in such a way that LG will end up looking like LTG. Just think about it. It's a pretty interesting thing to think about, that you don't really have two regular representations. Despite the fact that they look different, they're not really different. As I said, equivalent representations are not to be counted as different representations. Okay, quickly, let's just look at how to form the matrix for this. That's what we are going to be, which is going to be important to us. The regular representative of a particular group element, let's say GI, L-reg GI. Now, this is a operator. It acts on the vector space formed by AG. But of course, I would ask what it does to its basis. The basis, of course, is formed by the group elements themselves. So let's ask what L-reg GI does to a particular group element. Let's say GJ. By our rule, it produces GJ GI inverse, right? And what I want is to be able to write down the matrix like this. The regular KJ GI times GK. This has to be a linear combination of some of the GKs, and the linear combination will tell you what the matrix element is. And now, if I multiply GJ, remember, is a group element, although it's a basis vector for AG, but this is natural basis we are talking about. So we are using the original group elements themselves. So GJ is a group element. GI, of course, is an original group element. So what can you say about GJ GI inverse? What will it be? Will it be a combination of group elements or a single group element?
So
It has to be a single group element, right? Just because you have started talking about combinations now that you have this algebra AG, doesn't mean the original thing has changed. You multiply two group elements, you get a group element. So what can you say then about this DKJ GI? This remember is nothing but the kth column. Sorry, the jth column of the matrix, of the representative matrix. What can you say about the jth column of the matrix? The fact that GJ-GI inverse has to be a single group element and not really a combination, what does it tell you about the jth, about this column?
Delta.
Well, delta, okay, I guess I know what you mean. It essentially means that there's only one somewhere in this column. Everywhere else you have 0.
Yes.
Right?
Exactly.
In fact,
yes.
the rule is very simple. In fact, that works not only for rows, columns, it also works for rows, as you can easily argue. And what you really see is that this dkj-gi, okay, when will that be 1? That will be 1 only if gj-gi inverse is equal to gk, otherwise it will be 0. Or we just rewrite that gj-gi inverse equals gk, is if gk inverse gj equals gi. So if you want the regular matrix, regular representation matrix for a particular group element, all you have to do is ask this. Well, just form gk inverse gj, ask is it gi? If it is, then you get 1, otherwise you get 0. And the way to do that using the multiplication table is rather nice. So let me illustrate that to you. So this is the multiplication table for our group. This is exactly the multiplication table that we had worked out earlier. This table is of course written in the standard format, E, A, B, C, D, F, in that order along the rows. Okay, along the top row, which is of course each column is labeled by E, A, B, C, D, F, and each row is labeled by the same. But remember, what we want to do is gk inverse gj. If that's gi, I want to put a 1. So what I will do is I will write the multiplication table slightly different. Instead of labeling these, which are the ones which sit on the left for multiplication, instead of labeling these with the group elements themselves, we are going to label them with the group elements, but with the inverse of whatever is sitting here. So instead of using E, A, B, C, D, F, we are going to use E inverse, A inverse, B inverse, C inverse, D inverse, and F inverse. Will that change the multiplication table? If you paid attention, you would have noticed that the multiplication table did change from here to here. Can anybody tell me what changed? Not much, simply because of the 6 group elements that we are using in this case, 4 of them are their own inverses. E, A, B, C are their own inverses. So replacing E by E inverse, A by A inverse change nothing. But D and F, they're actually not their own inverses. D inverse is F, F inverse is D. So what has happened, if you paid careful attention, is that the last 2 rows and the last 2 columns got switched. Last 2 rows only, not the last 2 columns, because columns are still being labeled by E, A, B, C, D, F. Just the last 2 rows got switched. Okay. But the general rule is you just write down the multiplication table with the group elements labeling the columns and the inverses of the elements in that order labeling the rows. Now the job is simple. Suppose I want to find out, okay, can you spot one thing? What has happened to the E in the table now?
So the principal diagonal is
It's all E, right? Has to be, because that's exactly how we change the thing, right? E inverse, A inverse. So all the inverses are sitting on this side. So principal diagonal has to be all E's. And now the rule that we just stated simply becomes this. You want to find out the matrix for a particular group element, regular representation matrix. All you do is look up this table. Wherever that element occurs, put a 1. Wherever it doesn't occur, put a 0. So you want to find, remember there are 6 group elements, so 6 regular representation matrices. And I've just relabeled them with F and D. That was D inverse, F inverse anyway. So no real change. Now, all you do is find out where the E's are. The E's are all down the diagonal. So the regular representation matrix for E is, well, no surprises at all, once down the diagonal. What about the regular representation matrix for A? Simple. Just look at where the A's are in this table now. Just put ones there, put zeros everywhere else. B's C's, D's, and F's. That's it. You've got your 6 regular representation matrices ready and at hand. Okay? Of course, you have 6 regular representation matrices simply because it's a 6-dimensional group. If it's an order 6 group, if it had been a 10 order 10 group, then there would have been 10 by 10 matrices in the regular representation. But the rule would have been the same. Just write down the multiplication table with inverse group elements here and the group elements here, and just find out where in the final table the different elements are. They will tell you the regular representation. But can you tell me one thing? One very important quantity which is going to be very useful for this is something called the character of a representation. We will soon see that characters of representations are very important for calculating various useful results. The character is nothing but a trace of a matrix. So character of a representation means take every one of the representative matrices, take their traces. Can you tell me what is the character for the regular representation for this particular group?
0.
Well, it's 0 for this particular group element.
Yes.
But for the group as a whole, that means you have to tell me what is the representation for every one of the group elements. So is there any group element for which the character is not 0?
E.
E. And what is the group element? What is the character for that?
6.
Right. 6 in this case is actually the order of the group for every group, right? So regular representation has a character which is very, very peculiar and simple. This identity element has a character of mod G. Every other element has a character of 0. This is going to be very important in the next lecture. Okay. Now, one more thing. I'm actually out of time, so I will just take 2 minutes to, not 2 minutes, 5 minutes extra today to just wrap up this topic of unitary representations, which is given a linear operator. How do you define a unitary operator? I'm pretty sure all of you know this. If you have an inner product, that is, if you have a rule like this, how to associate 2 vectors to a real or a complex number, then the adjoint of a linear operator is defined this way. If T acts on V2 and you take an inner product with V1, if you move the operator from the right to the left, you get a new operator acting on V1. That's called the adjoint, T dagger. So T dagger is basically defined to be that new operator such that T dagger V1's inner product with V2 is always the same as V1's inner product with TV2. And of course, adjoint operators are extremely important in quantum mechanics, but they are important all over mathematics. And an operator is said to be unitary, again something which most of you would recognize from quantum mechanics itself, is if its inverse is the same as its adjoint. So U dagger U is identity. Then you say the operator is unitary. And you say a group has a unitary representation if every element, if it's possible to find a representation, or, okay, let me just rephrase that. You say a particular representation of a group is unitary if every one of the linear operators representing the group elements happen to be unitary. So all the LGs, if all of them are unitary, then LG, that is LG dagger LG is identity for every one of the LGs, then you say that you have a unitary representation. Unitary representations have many nice properties, and it's nice to know this result. That if you are on a finite, if you have a finite group, and you have an inner product space V on which you are talking about representations, then a particular representation may or may not be unitary, but it always is equivalent to a unitary representation. That is, if you have a finite group, then you can actually stop worrying about non-unitary representations, because if your given representation, even if it is non-unitary, you should be able to find the representation by unitary operators. The proof of this is pretty useful and interesting, but we are going to skip that for want of time. But the important notion is every group, every finite group has if it's defined, if it has a representation defined on an inner product space, because without the inner product you cannot even talk about unitarity. But if you have a representation defined on an inner product space, then that representation, if it is not unitary itself, is at least equivalent to a unitary representation. And since we don't count equivalent representations as different representations, we will simply use the unitary representation as and when needed. Okay, so the proof here is straightforward, but I'm not going to go into the proof right now. Okay, I think I will call it a day here as far as this part of the lecture is concerned. I still didn't finish all of what I wanted to say. So,
hello, sir.
yeah. Now
I have a question.
Questions. Yeah, go ahead.
So, you talk about the original, representation before, and you went to regular representation. My question is, what was the need for this regular representation?
No, wait a minute. I think I misled you in some sense somewhere.
Yes, I missed some.
I didn't say original represent. There is no original representation. A group may have many representations. Okay.
Okay.
And depending on your situation, one representation or the other may be important for you because it may represent some physical or entity. But there are many representations. In fact, there are infinitely many representations for every group.
Yes.
Okay. And what I did show is that the same group S3 has one-dimensional representations. All of them are one. That's one-dimensional representation. In fact, it has another one-dimensional representation. All the rotations are +1, all the reflections are -1. That's another 1D representation. Then I showed you a 2-dimensional representation. I showed you a 3-dimensional representation using the homogeneous quadratic functions. I just say that if you use the homogeneous cubics, you would get a 4-dimensional representation. And regular representation is a representation for which you do not need to think of some other vector space on which the group acts. Every group acts on groups from the group itself. So using that itself, just using the definition of the group and no other structure, you can actually construct a representation which is called the regular representation. It's one of the many representations that a group has. It happens to be useful simply because big representations can be built out of smaller ones called irreducible representations. That's going to be a topic of the next lecture. The regular representation is not an irreducible representation, but it is guaranteed to have all the edepth possible of the group in it.
Okay, so it is a more general form of.
Saying more general is wrong. It's a specific representation.
Okay.
It just happens to have the property that it contains within itself all the edepts a specific number of times.
So we find, sir.
That's not the only one. There are many other possible representations which have all the edepts. Or some will have only edepts, some will have multiple copies of the same edept, and so on. That will be the topic of the next lecture.
Okay, sir. And so we find the character of the representation for the regular one. For the regular representation, is it possible to?
You can find the character for every representation. In fact, the rule is just the trace.
Okay.
You have a representation, take the trace of every group element. That's the character.
Okay, sir.
The only thing so maybe because I talked of the character in the context of the regular representation, that sort of led to this confusion. Every representation has a character. For a 1D representation, the character is the same as just the group element or the representation, right? Because these are just 1x1 matrices then.
Yes, sir.
But for higher dimensional representation, the character is the trace of every one of the matrices. Now, for the regular representation, you have this very special choice that only the identity has a non-zero character exactly equal to the number of group elements. All other characters are 0. You will see soon that the character of a representation is very, very important because it can help you decide whether a particular group is reducible or not, whether or if it is reducible, how many copies of different irreducible representations it has, and so on. Everything can come out. In fact, almost all the calculations you do using group theory in chemistry, for example, at least using finite group theory, essentially uses characters and some results with characters.
Okay, sir. Thank you very much.
Okay. So any other questions?
Sir, for the linear operator, you have told us the SGI and SIJ thing when it is operating on the basis vector. Can you please tell us shortly?
What? I didn't understand.
Sir, why the J is before the I, SGI?
So you mean for a general linear operator TEI, you want to find the matrix for that? TEI, of course, are basis vectors, right? So TEI is a linear operator acting on a basis vector, has to be a vector, and every vector can be expanded in the basis, right? There's no question about that, right? J equals 1 to n, where you're in an n-dimensional vector space. The only question is why MGI and why not MIJ, right? Is that the question?
Yes, sir. This is my question. Why not I?
Okay, so for this, let's just look at, this has nothing to do with group theory. Let's just look at two matrices, two linear operators, S and T, and let's say S corresponds to, okay, let's say S corresponds to MS and T corresponds to MT. Okay, so MS is a matrix for S, MT is a matrix for T. So let's see what happens when ST acts on EI. And using that, we will find out the matrix corresponding to ST. So what does ST acting on EI mean? It means T gets to act on EI first. So S sits aside until T gets to act on EI. You get EJ, MT, the matrix corresponding to T.
Sir, I cannot see this.
Have I lost your connection again?
Yes, I cannot see the screen.
So presentation has stopped again.
Your presentation is not there.
Yeah, but again, was it not there for a long time or just now?
No,
Just now.
Yeah, my presentation stopped for whatever reason. Let me just check one thing. Yeah, I still have 10 minutes or so. Now
It is back.
Okay. Somehow the presentation stopped. Okay, let's. So you got to see this, right?
Yes, yes. Now it is.
Okay, let me just write this again so that you can see this a bit more clearly. This is S, the linear operator acting on TEI, and TEI, of course, as by the rule that we have written down, is MT JI EJ. J going from 1 to n. Okay. Now, this of course was your question. Why MTJI and why not MTIJ? But let us for the timing stick to the rule. The rule is MTJI and see what consequences it has. What happens after that? This S acts on this, right? S is the linear operator. On this side, these are numbers. This is the vector, right? So what will S do? It will simply jump across the MTJIs, go and hit S, right? And you get SEJ. Is it okay?
Yes.
Oops, where did I go? Oh, I wrote somewhere in the middle. Let me just put a new page after this. Okay, maybe change of color may be good. So this is going to be I'm confusing myself with my own notations, but this is MS. The matrix corresponding to the but S KJ EK, right? Is it okay? I've just used the rule again. The matrix corresponding to S is MS, and MS KJ EK is going to sit here. Now notice that this is of course a combination of the vector Ck. What combination? The coefficient in front is this, j equals 1 to n. This thing in red times this thing in blue. But if you want to make this into a matrix multiplication, what do I need to do? The column index for the first matrix should be same as the row index of the second, right? So I should actually move things like this. Everybody with me so far? Notice MTJI and MSKJ are just numbers. You can of course move them around. But the reason why I'm writing it like this is that now you can see that this is really a matrix multiplication now. And what's the matrix multiplication you're doing? MSMT, that matrices, AIS element EK. So notice that what we are essentially ended up with is, if S is represented by MS and T, the linear operator, is represented by MT, then ST, the product linear operator, which essentially means do T first, then do S, is represented by MS times MT. So the matrix multiplication reflects operator multiplication. This happens because of this change of order. If you did not change the order here, if you had written, if instead you have taken, let's say, if instead you had taken this, let's say, then I would urge you to think about this. It will be pretty easy to see that what will happen is then, if this were the rule, then TS would correspond to MSMT. So matrix products would have to be multiplied in the opposite order than the order in which the operators are written. That is why you need a switch here. And okay, maybe there's another way to see this, another way which makes this a bit more relatable to what you already know. A vector, of course, is not just the basis vector, right? A vector is a bunch of numbers vi. So these are just numbers. And these are the vectors, right? So when a linear operator T acts on V, what happens? Okay? But if you use our rule that we had right now, what does this say? This says the matrix M, Ji, Ej, sum over J. So now, if you just think about it a bit, the coefficient of the, after you apply the T on V, the coefficients can also be, you can think of this as changing the basis vectors, because after T will go and act on the basis vectors, or you can think of keeping the basis vectors the same EJs as before, but changing the coefficients. So instead of V, now you have V prime. So V prime I is MJI Vi summed over all I. Now this, of course, is the familiar rule by which matrices act on coefficients, right? The point is, if you want to keep the rule by which matrices act on coefficients, then the rule by which matrices act on basis vectors have to be the opposite. There's no mystery here. It's just that the rule that you always knew, that matrix multiplication goes as Mij, Ej, where Ej were not the basis vectors, they were numbers, they were the coefficients. So you actually knew the matrix version of an operator like this, perhaps. This term, Mij, Cj. There is no conflict between this and what I said right now. They are the same rule. But here you are saying this is what happens to the basis vectors. There, in here, what you are saying is this is what happens to the coefficients. Okay. Just think about it a bit. It's really, the difference really is because of that. And in linear algebra, it's actually more important to think about what happens to vectors than what happens to the coefficients, which are really artificial numbers. Okay, any further questions? Because there will be another one which will start soon.
Sir, in your next lecture, would you take a little attention to dagger function and all this stuff? Inverse
What?
dagger operator and the physical
Sorry, I
aspect.
couldn't.
So in the
What
coming
operator?
lecture, will you cover a dagger operator and inverse
Dagger
and
operator?
yes, sir.
You mean adjoint?
Physical.
They mean ladder. Yeah.
Ladder operator. Ladder.
Yeah. It's not
Yeah,
dagger.
well, ladder, right. Not in the coming lecture. Ladders come in the algebra section. Now here, okay, I'm in a rather embarrassing situation right now. Because at the rate at which I'm going, if I keep on going at this pace, I will finish the finite groups in 5 lectures instead of 3, which I wanted to. And in fact, there's not much wriggle room because 3 are already gone. So
Yeah, we can give you one extra lecture if you do not mind.
I don't mind, but even with 1 lecture, I can't really do all of Lie algebras or Lie groups. But I will try to sort of at least show Lie algebras and something about the ladder operators. Okay, but when can you give me the extra lecture?
I think it is on 6th. I have to check and get. 6th is.
Fifth, 4 o'clock.
5th, right?
Yeah.
5th, 4 o'clock. It's not 6th, it's 5th.
5th is okay. 6th, I have a class.
Okay, 5th,
I have a
4
class in the
o'clock.
morning, but okay, then I can manage that also. Okay, I think I should at least say something about what I promised. So otherwise, this is getting very embarrassing because at this rate, I can actually steamroll through the rest of the stuff and finish everything, but then nobody will understand anything. I don't think that's a good idea.
Yeah. Like actually, if most of the participants demand and if you agree, we can arrange for some extra lectures also. But that already that really depends upon you first, and then the demand. So
it depends more on the demand, right? Because
I'm there to
since I'm at home, I can. Okay, I can find some time here and there, but frankly, I'm not even sure whether they will need those lectures because most of the other parties, other speakers, will also talk about various topics, right? In fact, I think many of these things will also be covered.
Yeah, that's true.
Maybe
but you decide. I mean, decision is yours.
So maybe, okay, that can be decided even after the workshop. For example, if after the workshop enough people want, and such things have not been covered, we can fix up some other time.
I can do it.
We can have a small series. I have no problem.
That lecture on 5th, 4 o'clock is confirmed, right?
5th, right? Okay, then it's fine.
Yeah,
5th is fine.
Yeah.
Okay. And my next lecture is at 6, right? But I think I should really sign off now because somebody else is going to start at 4.
Yeah, sure. Sachin is there already, I guess.
Yeah. Okay. And the link is just the same as this one, right?
Yeah, it will remain same. All classes will have same link. Participants seems to be very confused. I have written it clearly in their mail, but they are not reading. So they are repeatedly sending me mails. But it's the same link valid for every day.
No, Google allows you to have the same link for 30 days or so, or even more.
That is why there is no point changing it again and again, right?
Right. Okay, I may stay logged in because I would want to listen to the next lecture as well, but maybe I will come back after a while. Anyway.
Okay, sure. We will have a 10 minutes break. Everyone needs a break, I guess.
Yeah, everybody.
So we can assemble here at 4 o'clock. You can take a break. You can have water, go around and come back. Because we are having the next speaker in the next lecture. Okay, see you after 10 minutes. Bye.